Good morning, students. In electromagnetic induction, we are going to study today motional electromotive force. Motion, that means in circular motion, and in that motion we have to find out the magnitude of electromotive force EMF. First case we are going to study, that is translational motion of a conductor. When the conductor is in translational motion, in that case we have to find out the electromotive force in that conductor. So this is the main setup of translational motion of a conductor. In this diagram, a rectangular frame, see, this is shown by the red chalk. This is the rectangular frame. The plus sign is the magnetic field. Plus sign, circle with it. It is the magnetic field into the paper. As shown in figure, a rectangular frame A, B, C, D. A rectangular frame of wires A, B, C, D of area Lx. This side AD has a length L and side AB has a length X. And area of this rectangular frame is Lx. Is situated at a constant magnetic field. This field is the constant magnetic field, and magnetic field is denoted by vector B. As wire BC, as shown in figure, observe this figure, wire BC of a length L. This wire BC having the length L is move out with a velocity v. Is move out with a velocity v. That means this side BC is a movable. We can move this side in front or backward side. So this side is a movable. We can move. When we move the side BC, the length is increased. The length, that means this distance x is increases. As the wire BC of length L is move out with a velocity v, to increase x. To increase this distance x, the area of the loop A, B, C, D also increases. As the area increases, the flux of B, the flux of magnetic field B through the loop, through this loop, is also increases with time. As this length increases, area of the loop also increases, and as the area increases, the magnetic flux of this loop A, B, C, D also increases. According to flux rule, last lecture we studied the flux rule. So according to flux rule, the induced EMF will be equal to the rate of change of magnetic flux. Rate of change of magnetic flux through the conducting circuit is changing. According to flux rule, the magnetic flux is changing with respect to time. So as the flux is denoted by phi. Flux is denoted by phi. area of the loop. A is equal to L into X. So magnetic flux, that means total magnetic field lines passing through that area, which is equal to B into A. Magnetic flux is equal to B into A, and the value of A is L into X. So magnetic flux phi is equal to B into Lx. Therefore, magnitude of induced EMF, magnitude of induced EMF, magnitude of induced EMF, we can write as mod of E. We write only magnitude. Therefore, mod of E is equal to d phi by dt. Mod of E is equal to d phi by dt, which is equal to d by dt. We know the value of phi. Value of phi is d L into X. Substitute this value in this equation, d L into X. So we get, which is equal to d is the constant, d L is constant, and d x by dt, dx by dt, which is equal to d L. We know that dx by dt, distance with respect to time, is velocity v. Therefore, we get the magnitude of induced EMF in this loop is equal to B L into v. This v written in short letter, small letter, because we always show velocity with a small letter. So E is equal to B L v. We get this value of electromotive force in this loop. We give this equation as equation number 1. Now observe in diagram. We get this velocity v is the velocity of wire BC, increasing the length x. Increasing the length x of wire AB and CD. Now a charge Q which is carried along by the moving wire BC. A charge Q which is carried along the wire BC and experience a Lorentz force. This side BC carries the charge Q. Charge Q is denoted by small q. So by Lorentz force acting on this side BC, we get vector F is equal to Q multiplied by P into D. F is equal to force acting on this side BC and charge F is equal to Q into P multiplied by P. Now P velocity and its magnetic field is perpendicular to both velocity phi. This phi and B. Phi and this magnetic field is perpendicular to this side BC and the charge Q. Charge Q perpendicular because this charge is induced or is produced in this side, in the side BC, but its direction is parallel to the side BC and perpendicular to this magnetic field. So the force F is constant. This force F is constant along the side N of the wire BC. So when the charge Q, this charge Q moves a distance L along the wire, this charge Q moves with a distance L along this wire, the work is done by the Lorentz force. And we know that work is denoted by work is equal to F multiplied by L. Force into displacement. Work means force into displacement. So, seeing this diagram, the side BC is movable, and by this movement, the force acting on this side is F. So, we get the work done by the charge W is equal to F dot L. Force into displacement. Displacement is F. So, we get the value of F. F is equal to Q multiplied by V into B. V, vector V multiplied by vector B. So, substitute this value in this equation. We get W work done by the charge. W is equal to L into Q into vector B multiplied by vector B. If we write this equation in a magnitude, we get W is equal to Q L B into V into sin theta. Q L B V sin theta. This is the equation we get work done for the charge. Now the EMF is generated. We have to find out the electromotive force, the value of EMF, because we write here translational motion of a conductor, and conductor is a rectangular frame, and this side BC is movable. In this frame we have to find out the value of EMF. So up to this we get the work done of this frame. Now we have to find out the EMF of this loop. So we know that EMF is generated work per unit charge. So EMF is equal to work done per unit charge. So substitute the value of work here. Q L B V sin theta divided by Q. What is the value of work we get? Q L B V sin theta divided by Q. Q and Q get cancelled. So we get the value of E is equal to B V L sin theta. What do we get? E is equal to B V L sin theta. B is the magnetic field, V is the velocity of this side BC, L is the length of that side, and sin theta, theta is the angle between them. So if theta is equal to 90 degree, then we get the maximum value. Of EMF. Emax is equal to B L V. We get the maximum value of EMF. Emax EL3 and Emax is equal to BL3 is the same equation. So derived from the rate of change of flux, if it can be proved that for any circuit from these two equations, we can prove that for any circuit whose parts move, in a fixed magnetic field, the induced EMF is the time derivative of flux. The induced EMF is the time derivative of flux is equal to BL and we know that P is equal to dx by dt. That means in translational motion we get the value of EMF as the induced EMF is equal to time derivative of flux for any circuit. We consider as this rectangular frame A, B, C, D placed in a constant magnetic field. As this white plus sign is denoted as a constant magnetic field. So it can be proved that for any closed circuit whose parts move in a fixed magnetic field, the induced EMF is the time derivative of the flux. So we get E is equal to BL3 when there is a translational motion of a conductor. This side BC has a translational motion. That means this side BC will move in front or in backward direction. This motion of this side BC is translational. Now second point that we are going to study, that is motional EMF in a rotating bar. This is the translational motion of a frame. Next equation we have to find out, that is motional EMF in a rotating bar. B EMF in a rotating bar. For this, there is a slight change in the diagram. Now the bar is rotating. For example, this is the conducting bar. Having the length L. Consider in that there is a small segment. This is a conducting bar and having length L. In that conducting bar there is a small segment. For the small segment we denote it as a dr. For a small segment. Now, this is the magnetic field as shown here. B is the magnetic field. This distance is R This is the v means velocity. V means velocity, and from this point, small segment dr, this distance is r. This distance is r. And this bar is balancing point. This rotating bar is a balancing point. We call it as a pivot. We call it as a pivot. So, as shown in diagram, this is the rotating bar. We consider a small segment in that bar dr. The rotating bar has a length L. The small segment dr. Now this bar is rotating. So this displacement with respect to time will get velocity in this direction. From the small segment, this distance is r, and plus with a circle is the magnetic field B into the paper. And in this rotating bar, we have to find out the value of E. We have to find out the value of E, electromotive force. Electromotive force. So, a conducting bar, as told you, a conducting bar rotating around the pivot. Pivot, that means the point, the central point on which it balances. We call it as a pivot. Of one end in a uniform magnetic field that is perpendicular. That is perpendicular to the plane of rotation. This conducting bar is perpendicular to this magnetic field. It's perpendicular to the plane of rotation. A rotational EMF is induced in between the end of bars. The rotational EMF is induced in between the end of this bar. Now, a rotating bar is different in nature from the sliding bar. जसं आपण फर्स्ट एक्झाम्पल मध्ये पाहिलं, ट्रान्सलेशनल मोशन मध्ये पाहिलं की तो जो बार होता, आपण एक साइड जी आहे ते आपण मूव करत होतो. दॅट मीन्स स्लाइड करत होतो फ्रॉम वन पॉइंट टू अनदर पॉइंट. नाउ दिस rotating bar is different nature than the sliding bar. Consider a small segment dr. Now consider, we have to consider a small segment. For example, this is the rotating bar, and in that rotating bar, this is the small segment dr of the bar at the distance r from the pivot. It is short length dr of a conductor which is moving with a velocity v in a magnetic field B, and has an induced EMF generated in it like a slide bar. When this conducting bar is rotating, the EMF is induced in that rotating bar. By imagining, we have to imagine all such segment. Which segment? This small segment. We call it as a dr. So, by imagining all such segment as a source of EMF. So, we have to find out all these segments are in series. These segments are in series, and therefore the EMF of individual segments will be added. That means we find total EMF of this rotating bar. Then we have to add all these segments whose distance is dr. We have connected in a series. R2, this segment is the R3. For total EMF, we have to add all these segments from this point to end point of the rotating bar. So, for a small segment DR, the induced EMF for small segment DR, for a small segment DR, the induced EMF is also small because this distance is small, and for this distance the induced EMF is also small, and we denote it as a dE. For a small displacement, the induced EMF is also small, E, dE. E for induced EMF and dE, smallest induced EMF for the segment DR. So, dE of the rotating conductor. Therefore, dE is equal to P phi into dR. We know that E is equal to BL phi. E is equal to BL phi. But for a small distance, dE is equal to B phi dR. So, by adding this dR, that means we get total induced EMF in the rotating rod, in the rotating bar or rod. E is equal to integration of dE. E is equal to integration of dE, which is equal to integration of, what is the value of dE? B phi dR. B phi dR, and value limitations is from the bar length is L, 0 to L. Limitations is 0 to L. So we get E is equal to B integration of B taken outside, integration of 0 to L phi into dR, in integration phi into dR. Now this bar is rotating. Observe the diagram. This bar is rotating, and in rotating condition we get the velocity, angular or rotating velocity, and we denote it as a omega. And we know the relation between phi and omega. Phi is equal to R into omega. This is the translational velocity, this is the rotational velocity. So, substitute this value in this equation. E is equal to P integration of 0 to L R omega dr, which is equal to B omega taken outside, integration of 0 to L R into dr. Integrating it, B omega in bracket L square divided by 2. Lower limit is 0. So the next step is minus 0. So we get E is equal to 1 half B omega L square. E is equal to 1 half B omega L square. B is the magnetic field, omega angular velocity or rotating velocity, and L means the length of this bar. So we get the value of EMF in a rotating bar is E is equal to 1/2 B omega L square. This L we get here L square. Now comparing this equation with the first equation that we get in a translational motion of a bar, that means E is equal to B L into V. For a closed loop, if the bar or one side is movable, then we get the value of EMF. E is equal to B L V. The constant magnetic field. L is the length of that side and V is the velocity. And in rotational motion, we get the value E is equal to 1/2 B omega L square. That means in a rotating bar, in a rotational motion, listen carefully students, in a rotational motion of a bar, when kept in a magnetic field, we get the double value of EMF than the translational motion of induced EMF. Here we get, for example, here is the 100 value of this E. Then in translational motion of the loop, we get the value of E is equal to 50. So by comparing, this conclusion is drawn. We get here the maximum value than the translational motion. So in these points, that is the motional electromotive force, we get the value of EMF as E is equal to BLV for a translational motion of a conductor, and for a rotational motion we get E is equal to 1/2 B omega L square. So these two value of EMF for these two conditions we get. And the next point is induction and energy transfer. Induction and energy transfer. Induction and energy transfer. Energy transfer in a magnetic field. This induction and energy transfer, for this we have to consider a constant magnetic field. So consider loop A, B, C, D. We have to consider a loop A, B, C, D. A, B, C, D. A loop A, B, C, D kept partially in a magnetic field. The side BC is outside from the constant magnetic field, and the constant magnetic field is denoted by plus sign. Circle with the plus sign. So this is the constant magnetic field. A, B, C, D is moving with a constant velocity. This loop A, B, C, D is moving with a constant velocity V in a constant magnetic field as shown in this diagram. A current I is induced. A current I is induced. Current I is induced in the loop in clockwise direction, and loop segments, these loop segments being still in a magnetic field experience a force F1, experience a force, this force F1, F2 and F3, F1, F2 and F3. The dash line, for example, the dash line, this is the dash line, shows the limit of magnetic field. This dash line shows the limit of magnetic field. To pull the loop, for example, this loop A, B, C, D is pull the loop with a constant velocity towards the right. If we pull this loop towards the right side with a constant velocity, then it comes outside of this magnetic field. This loop, some part of the loop is come outside of this magnetic field. It is required to apply an external force. When we pull this loop, it requires apply an external force on the loop so as to overcome the magnetic force of equal magnitude acting in opposite direction. When we pull this loop A, B, C, D, pull this loop, there is applying an external opposite force, opposite equal magnitude but in opposite direction. So rate of we get the rate of force, rate of doing work done, rate of work done on this loop P is equal to rate of doing work done on this loop P is equal to work divided by time. P is equal to work divided by time, which is equal to force. Work means force into displacement divided by time. So we get P is equal to F into displacement R divided by time, and R divided by time is the velocity. So we get P is equal to F into V. P is equal to F into V velocity. We get this equation. P means power of the loop. P is equal to force into velocity. So up to this point we stop for today. Thank you.